Hi, I'm going to talk a little bit about Chapter 7 in the OpenStax Astronomy book, which is an introduction to the solar system, and kind of hit on some of the major points that's covered in there. So it starts off with section 7.1, which is just an overview of our planetary system. I'm not going to read you the slides because that's the most annoying thing, is when somebody just reads to you from a PowerPoint presentation. First of all, let's just sort of talk about what we mean by the solar system. Now, technically the more correct term for it is planetary system. We call our planetary system the solar system because at the center of it all, we've got our star, the sun, or Sol. Whereas other, planetary systems that are centered around a star, they're centered around a different star, so there would be a different name for it. So planetary system is really the more general term for a star and everything that's orbiting it. In our particular planetary system, at the center of it all, we have the sun. The sun takes up a fairly amazing amount of the total mass of our system. It's 99.8%, which means just 0.2% or just 1/5% is everything else. All the planets, all the moons, all the asteroids, comets, dust, everything. Surrounding and orbiting the sun, we've got 8 major planets that we have identified and classified as such. And if you notice in the diagram right here, those planets are depicted by these blue orbits. And one thing you note with all these orbits, they're more or less in the same plane of existence. That's what we refer to as the plane of the ecliptic. And that's one of the reasons why we define them as planets, whereas something like Pluto, who used to be classified as a planet, it has a very wild and erratic orbit that's not in that ecliptic plane. In addition to the planets, we have discovered close to 1,800 what are called trans-Neptunian objects, or TNOs, orbiting outside the range of Neptune. Some of the largest ones we've come to call dwarf planets. And of course, Pluto is the first one of those that was discovered, but there are several others, such as Haumea, Makemake, Eris, and numerous others either waiting to be discovered or that are not as large as these. We give a name to the largest of these. We call them dwarf planets, and Pluto belongs to them now. We also have several asteroids and comets that have erratic orbits. Many asteroids are located in a belt between the orbits of Mars and Jupiter. One of those in particular is the asteroid Ceres. And it's the largest of the asteroids. It's large enough to where we also consider it to be a dwarf planet. And should we ever end up colonizing further out from Mars outward, Ceres would be a really likely place to put some kind of a permanent establishment, some kind of a permanent station for further colonization and exploration. The 4 rocky planets that are inside the asteroid belt, and if you really want to get picky about it, you could include the moon as a 5th rocky planet, sometimes called the terrestrial planets. Again, that comes from the word terra, which means earth. So again, we don't want to get too Earth-centric when we're talking about these. But what they all have in common is they're all small, they're all dense, they're all made of heavier elements. All of them at some point in their existence have had some kind of active geological activity. They've all got evidence of some plate tectonics, mountains, volcanoes, erosion, weathering, and then many, many crater strikes. The 4 planets outside of the asteroid belt are referred to as the giant planets, whereas the inner planets are mostly made of heavier, dense elements. The ones that are outside are made of lighter elements. They've got very dense cores with lighter elements like hydrogen and helium surrounding them in these massive, massive, thick atmospheres. In addition to the planets, there are about 180 or more than 180 known moons, including our moon and including several named moons, but also including several other natural satellites around the planets. And then, of course, rounding things out, we've got dust. We've got cosmic dust orbiting in various packets and clouds around the sun. We've got some of that dust concentrated into the rings, which you find on the giant planets, Saturn being the most notable of those. But all of that is included as part of the planetary system. If you were to open it up and have a list in the box of all the parts, that's more or less a exhaustive parts list. Section 7.2 talks about the composition and structure of all these planets, and we're going to start with the gas. Well, we called them the gas giants, probably inaccurately, because the gas is the part that we see, because they do have very thick atmospheres, but it's much more likely that the interiors underneath those atmospheres are mostly made up of liquid or even solid forms of those lighter elements like hydrogen and helium. Jupiter and Saturn, the two largest planets, have ingredient lists pretty close to identical with the Sun. They're about 75% hydrogen, 25% helium, much like our Sun is. The only difference between them and our Sun is mass. Our Sun had so much more of this material that it was able to, underneath that pressure and the heat that came from it, it was able to achieve sustainable nuclear fusion, which is where all the energy in the Sun comes from. We think, and again, we're not entirely certain because frankly, we can't see through these atmospheres, and we have sent some probes toward these planets, but they've had limited success in determining what's further down underneath these thick blankets of atmosphere. We believe that there's liquid or even solid forms of these elements in a more dense region underneath the clouds. A lot of that is based on the gravity that they are seen to exert on not only their natural satellites like the moon, but also on any spacecraft we've sent their direction. Uranus and Neptune are not as large to the naked eye as Jupiter and Saturn, but that doesn't mean that their cores are any smaller. Their cores could be very comparable in size. The biggest difference is that they don't have as thick of an atmosphere as these first two do. Otherwise, they're built in pretty much the same way. Lighter elements around what's probably very dense liquid and solid cores. Moving in, we have the terrestrial planets. By contrast, these are made, instead of lighter gases, these are made of mostly heavier elements, including principally silicon, oxygen, iron. There's also quite a bit of sulfur, nickel, etc. And there's a little bit of a range. Mercury has a higher percent of metals to non-metals, whereas our own moon has very few metals in it. And a lot of that has to do with how we believe the moon was formed from the expelled early crust of the Earth after a big collision between two protoplanets. Whereas Venus, Earth, and Mars, they're chemically pretty close identical, give or take. They're generally about 1/3 heavier elements like iron, nickel, and to a degree sulfur, and 2/3 silicon and oxygen compounds, silicates, etc. One interesting thing that happened to all of these, well, these four anyway, is a process known as differentiation. If you were to take a sample at the surface of any of these rocky planets and then take a surface toward the core, it would be very, very different. And if they all came from rocks that were floating in space and then coalescing, you would expect it to be a little more homogeneously distributed. What we believe happened is that all of these at some point in their existence got so hot that they essentially became large molten drops floating in space. And when they were hot and molten, the heavier, more dense elements like your irons and your nickels and your sulfurs sunk toward the center of that drop's gravity and became the core. And then the lighter things, the less dense things like your silicons and your oxygens, made their way to the outside. Interesting things, and we'll talk more about what we believe to be true regarding the history of some of these planets. It's worth noting at this point that Venus and Earth are the only two of the inner planets that have any kind of atmosphere. In addition to that, moons, asteroids, and comets. Our moon is the only moon that we say its name with a capital M. Okay, just because it is our moon, it's Luna. Um, Other moons, and there are, like I said on a previous slide, there's 180 or more moons floating around. The biggest ones, Ganymede and Callisto, which are two moons of Jupiter, and Titan, which is the largest moon of Saturn, have a composition that's about 50% heavier elements, rocks and metals, and about 50% frozen water or water compounds. It's ice of some kind. Most of the other moons are much closer in composition to the cores of the planets that they orbit. Again, except for our moon Luna, who was formed, we believe, a little bit different than these other what we believe to be captured moons revolving around other planets. By contrast, asteroids and comets have, we believe, existed largely unchanged and undifferentiated since the formation of the solar system, which we are able, our best guess right now anyway on the date is somewhere around 4.4 billion years. Asteroids are mostly rock. Comets differ from them by being about half rock and half ice. Some missions that have flown to asteroids or to comets in an effort to try and retrieve some of their material and then return to the Earth have met with varying amounts of success, but we fully expect to find, whenever we gather additional samples from these, that they will continue to show a relative age of about 4.4 billion years, as do most of the other rock samples taken from within the system. Going back to the inner planets, we talk about geological activity, and again, that's a very Earth-centric term because geology literally means the study of Earth. But there's really not a better term that I'm aware of, except maybe tectonic activity, I don't know. But all planets, whether they're the inners or the outers, or even the dwarfs, have experienced bombardments. They've been hit by asteroids, they've been hit by comets, meteorites, as many of them continue to do. But the inner planets, because they do have rocky surfaces, they have maintained a record of those meteor strikes and those asteroid strikes and comet strikes with extensive cratering. We also have evidence on at least the Earth and Mars that there has been events like erosion, weathering, active geological activity like volcanoes, magma flows. And that all results from the inner planets having been molten at some point, having very hot inner cores. Now, out of the 5 rocky bodies toward the center of the system, the Moon and Mercury don't have any kind of active geology going on. Because they're much smaller than all the others, they are thought to have cooled down from the inside out much more quickly, so they don't have any plate tectonics, they don't have any liquid core left. On the other end of that, Earth and Venus do still have active geology and active heating going on inside and being radiated out, which is continuing to maintain things like a spinning metal core, which gives rise to magnetospheres, which protect the atmospheres of both the Earth and Venus from being stripped away by the solar wind and solar radiation. Mars is somewhere in between. Mars didn't cool quite as quickly as Mercury and the Moon, and that's evidence because Mars has some of the biggest volcano in the solar system that we know of, Olympus Mons. There's also evidence that Mars had liquid water because there's evidence of erosion and weathering, and that you're only going to get when you've got a water cycle of some kind going on. But again, because Mars was so much smaller than Venus and the Earth, it's thought that its core cooled and stopped moving, which would have then gotten rid of any kind of magnetosphere and any kind of protection from the sun. As a result, Mars today does not have very much of an atmosphere at all. There's no liquid water on the surface because there's no atmosphere to give it pressure enough to stay liquid, so any water just evaporates off, aside from some which is possibly frozen at the poles. Section 7.3 I'm not going to get too deeply into. It talks about some of the ways that we determine the dates of planetary surfaces, and the two big ones are by counting the numbers of craters that are present and looking at some kind of system of looking at rates of cratering, and also by analyzing rock samples that have been collected and using radiometric dating on them, which we covered quite a bit back in chemistry, talking about half-life and figuring out the age of samples based on that. Last section is section 7.4, origin of the solar system. Of course, one of the things about the origin of the solar system, if it happened 4.4 billion years ago, we didn't have any eyewitnesses or historical accounts, since we haven't been around anywhere near that long. And so when we try and figure out how the solar system came to be, what we have to look at is present state of things. And we have to sort of infer and work backwards based on the evidence we have to try and determine what could have caused it to work the way that it works. And so, for example, if you look at the solar system today, like I said, the 8 planets that we have are mostly in the same ecliptic plane. They revolve around the sun in more or less the same direction. Most of them rotate in the same direction, with the exceptions of Venus and Uranus, who actually has a sideways rotation. The sun itself also rotates in that same direction. Now, when we look at all of that spinning in the same direction, it's not hard to imagine that it all started out as a large cloud of hot gas and dust called a solar nebula. And that solar nebula, as gravity brought the densest stuff into the middle, it began to burn in nuclear fusion. And so the center of that mass and that gravity became the star. And as it continued spinning, other material outside of that began coalescing. Okay, gravity between the different bits caused it to stick, kind of like dust bunnies under the bed. And over time, the larger dust bunnies coalesced into planetary bodies, and smaller ones became some asteroids or crashed into the larger ones. Another thing that gives rise to the evidence of this is the chemical composition of the giants, being very, very similar to what we found in the sun, almost identical. And so that leads us to believe that there was some common formation, that it happened more or less at the same time throughout the early solar system. The pony, I was doing a search for images of solar nebulas, and somebody on Tumblr had a pony they drew named Solar Nebula, and that's her, and I just thought that was cool, so that's why she's here. Other patterns that we noticed, again, the inner planets being so rocky and so dense, and the outer planets having such thick atmospheres but being mostly lighter elements, what we can infer from that is that radiation and solar wind kind of blasted a good bit of the early atmosphere off of those inner planets, whereas it didn't happen to the ones further out. They didn't receive as much heat or as much radiation, so they were able to kind of keep hold of those lighter elements as gases and liquids. Whereas the inners, since they have heavier elements would have much higher melting and boiling points, would be able to survive being closer in, as well as having greater density. Their gravity would draw them closer to that center of the early galaxy. But aside from just looking inward, we also are able now to look outward. We're able to examine evidence from very far away. With increasingly more powerful telescopes, we've been able to observe far-off nebulae, large clouds of gas where stars are, or at the time that the light left them, they were being formed. And if you see here in the pictures, we've got example after example of early stars very early in their life cycle, and they are almost universally surrounded by some kind of clouds of gas or disks of gas, more or less like we would have expected to find 4.4 billion years ago or earlier in our own system. Interesting thing about these that we often forget is that when we see images like this, we are looking literally into the past. If you've got an object that is 100,000 light years away, then by the time light reaches us, what we are actually seeing happened 100,000 years ago. And the greater the distance, the farther back in time we're able to see. And so we're able to see these processes that we believe happened right here happening further back in time in these far distant locations. So anyway, in a nutshell, that wraps up the entire chapter in OpenStax Astronomy, and thank you for your time.